So today, we're going to talk about a totally different kind of AI. Not the kind that's writing poems or making funky pictures, no. This is an AI designed from the absolute ground up to run the most critical, most high-stakes physical systems we have. We're going to break down its hidden architecture. And to really get why this new approach is so critical, we have to start with a question that sounds like pure science fiction. Can you actually trust an AI to control a nuclear fusion reaction? I mean, to literally contain a small star right here on planet Earth? I mean, just think about the environment we're talking about here. A Tokamak reactor. It's running at 150 million degrees Celsius. That is 10 times hotter than the core of the sun. The magnetic fields you need to bottle up that plasma, they're powerful enough to literally lift an aircraft carrier. In a system like this, there's just no room for error. Zero. So, can the AI we all know and use, the kind on our phones and our web browsers, can it handle this? The answer is an immediate hard no. Not a chance. And it's not because it isn't smart enough. It's because it has a deep, fundamental, and honestly dangerous blind spot when it comes to how the physical world actually works. And that gets us to the absolute heart of the problem we need to unpack today, this dangerous 3D blindness. It's the core reason that the AI we see everywhere is totally unequipped for real-world engineering challenges. All right, here's the fundamental issue. For a standard large language model, everything, and I mean everything, a word, a complex idea, a physical object like an airplane wing, it all gets flattened down into a one-dimensional list of numbers. It's just a long string of statistics called a vector. There's actually a great name for this. It's called the Slob the Dachshund problem. Here's how it works. You ask a standard AI to draw a dachshund from the side view. It'll probably look perfect, right? Because it's seen millions of pictures of dogs from the side. But then ask it to rotate that same dog 45 degrees. Suddenly, it's a total mess. You might get a tail coming out of its nose. Why? Because the AI has no real concept of three-dimensional space. It's just memorized a bunch of flat views. So you see the massive disconnect, right? On one hand, you've got standard AI. It sees the world as a flat list of stats, and it fakes any understanding of space by just memorizing patterns. But on the other hand, you've got physical reality, which is, a 3D geometric structure that has to obey the unbreakable laws of physics. You can't just fake it when people's lives are on the line. So that's the problem. What's the solution? Well, it starts with a completely new way of thinking. You have to build an AI that doesn't try to fake physics, but instead is designed from the beginning to speak the native language of physics. And that solution is called geometric AI. It's a total game changer. Instead of flattening the world, it uses a special structure called a graph neural network, or a GNN, to build an internal model of the world that gets 3D space, that gets shape and direction right from the very start. Okay, to make this super simple, let's use an analogy. Think back to high school gossip. You can think of each student as a node in a network. The relationships between them, who's friends with whom, those are the edges. An information, or gossip, passes along these edges. Some of that info is a scalar, just a simple fact, like Andy got a 42 on his test. But other info is a vector. It has direction, like Abby walked left. And believe me, that difference between scalars and vectors, it's everything. Scalars are invariant. They don't change when you look at them from a different angle. The temperature inside a car engine is the same no matter which way the car is pointing. But vectors are equivariant. They have a direction that has to change when the system rotates. The wind's velocity has a different direction if you turn your map upside down. Geometric AI is mathematically designed to understand and respect this difference perfectly. And does this actually work? Oh yeah, this isn't just theory. Because this architecture truly understands 3D forces, it's been used to predict chaotic, dangerous airplane turbulence with 98% accuracy. And it's the exact same principle that's key to keeping that superheated plasma from escaping a fusion reactor. Okay, but, and this is a huge but, getting the right answer is only half the battle. In the world of high-stakes engineering, it's just not enough. You also have to be able to prove, without a shadow of a doubt, how you got that answer. This really gets at a fundamental rule of engineering. Just because your model worked one time in a lab experiment, that doesn't mean you can certify it to run a nuclear power plant. Regulators, engineers, and really all of us, we need verifiable, transparent proof that the system's logic is sound. And the author has a really personal story that drives this home.
He was on a research project where the math was correct, the experiments confirmed it, but their grant application was rejected. Why? Because they couldn't systematically prove why their chosen mathematical formula was the right one over any other option. And the takeaway here is so important. Without explainability, accuracy is basically useless.
So how do you actually solve this trust issue? How do you build in that proof? Well, you build a system that does all of its heavy thinking ahead of time. A system that can prove its own math before it ever gets near a piece of critical hardware. This is where the second huge breakthrough comes in. It's a system called XRAG, the Extreme Reliability Axiom Generator. I love this analogy. Think of it as an offline detective. It takes all the data from a physical system, but instead of just reacting in real time, it works methodically behind the scenes to find the single best mathematical explanation for what's going on. And it follows this really clever 5-step process. First, it characterizes the data to understand its core mathematical properties. Then, it pulls every possible mathematical tool it might need from a huge library. Now, here's the crucial part. In step 3, it filters out all the tools that simply don't match the data's properties. After that, it fine-tunes the best one left, and finally, it spits out a human-readable report explaining exactly why it made the choices it did. Let's make this real. Take the nuclear sensor problem. For years, human engineers have defaulted to a standard tool called a Fourier transform to analyze sensor data. But XRAG's first step, characterization, immediately sees that the reactor data is non-stationary. It's messy and it changes unpredictably. The Fourier method assumes the exact opposite, which makes it the wrong and potentially unreliable tool for the job. And here's the result. It's just, wow. XRAG automatically tosses out the flawed Fourier method and mathematically proves that a different tool, a wavelet transform, is the superior choice for this specific data. And just by making that one provable choice, it slashed the data scatter, which is basically a measure of unreliability, by a whopping 67%. So, okay, let's zoom out. When you put these two pieces together, the AI that understands 3D physics and the engine that can prove its own math, you unlock something truly incredible. You get the ability to start simulating tomorrow's failures today. It's this idea of a world model. And what that means is an AI that can run millions of what-if scenarios based on the actual laws of physics. It can ask, what if this bearing starts to wear down? Or what if this magnetic field fluctuates by 0.1%? And it can see the cascading consequences play out in a perfect simulation long before it ever happens in the real world. And that's really the final question I want to leave you with. What actually changes when the machines that run our world, our power grids, our airplanes, our factories, gain the ability to perfectly simulate and understand the physical consequences of their own actions before they even move a single millimeter? That right there is the future this architecture is being built for.